In this lesson, we will cover Hess's Law and how it can be used to determine the enthalpy change for virtually any reaction. Simply, Hess's Law states that the enthalpy change of a reaction is the same regardless of the number of steps involved. This means that the path reactants take to reach their final product does not affect the overall enthalpy change. Whether it's a one-step process or five-step process, the enthalpy change will be the same. This also means that enthalpy is what's called a state function, as state functions don't depend on the path taken. So since a multi-step reaction will have the same overall enthalpy change as a one-step reaction with the same reactants and end product, we can use this to manipulate and add multi-step reactions to determine overall enthalpy changes. When manipulating thermochemical equations, however, there are a few rules to follow. Firstly, when you reverse a reaction, you must change the sign of the standard enthalpy change. Thus, if a reaction is endothermic, meaning it absorbs heat, then the reverse will be exothermic and release heat. Secondly, if you multiply the reaction by a number n, then you must also multiply the standard enthalpy of that reaction by n. Lastly, when reactions are added together, so are their standard enthalpy values. Let's look at an example of this. Let's say that we want to determine the standard enthalpy change of the following reaction. We are given the following two reactions to help in our calculation. Firstly, we have the equation for the formation reaction of carbon dioxide, which has a standard enthalpy of formation of negative 393.5 kilojoules per mole. Secondly, we're given the equation for the formation of H2O. This equation is 2 times the standard formation reaction of H2O, as 2 moles of H2O are produced rather than 1. The standard enthalpy change of this reaction is negative 483.6 kilojoules per mole. So let's see how we can manipulate these equations to get our desired equation. Our first equation, the formation of carbon dioxide, has solid carbon as a reactant and carbon dioxide as a product in our desired amounts. So we can leave this equation as is, also leaving the enthalpy change the same. Now on to the second equation. The equation for the formation of water does have H2 gas and H2O gas in our desired amounts, but they are on the wrong sides of the equation. Thus, we must reverse this reaction to get them on the right sides. Doing this means we must also change the sign of the enthalpy change, giving us positive 483.6 kilojoules per mole. We're now ready to add these equations together. We can see that we have oxygen gas as a reactant in the first equation and as a product in the second equation, which means they will cancel each other out. Now, adding up our two steps, we get our desired equation. Adding up the enthalpies, we get an overall enthalpy change of 90.1 kilojoules per mole. This tells us that the standard enthalpy change of our desired equation is 90.1 kilojoules per mole of solid carbon. Now, in this example we just did, we used the equations of multiple formation reactions to obtain our desired result. This technique can be used for any reaction. Hess's law tells us that the change in enthalpy for any reaction is equal to the sum of the enthalpy of formation of all the products minus the sum of the enthalpy of formation of all the reactants. We can write this out as an equation. The standard enthalpy change of a reaction is equal to the sum of the number of moles of each product multiplied by the enthalpy change of each product minus the sum of the number of moles of each reactant multiplied by the enthalpy change of each reactant. Let's go through a quick example. We have been given the following equation and must determine the standard enthalpy change. We'll begin by writing down our equation. Now we can substitute the variables with our information, starting with the sum of enthalpy of formations of our products. Our first product is carbon dioxide gas, which has a standard enthalpy of formation of negative 393.51 kilojoules per mole. Since there's only 1 mole of carbon dioxide in our reaction, we just write negative 393.51. Now to add our second product. H2O has an enthalpy of formation of negative 285.83 kilojoules per mole. Since we have 2 moles of H2O in our reaction, we'll multiply this by 2. Now to subtract our reactants. Our first reactant, CH4, has an enthalpy of formation of negative 74.81 kilojoules per mole. Since there's only 1 mole of CH4, we don't need to multiply this. Lastly, we have oxygen, which is an element, meaning it has an enthalpy of formation of 0. Performing this calculation, we get an overall standard enthalpy change of negative 890.36 kilojoules per mole of CH4.